Welcome to Study Loop.
42.22, we want to take an alpha particle apart, maybe with some very small tweezers or something. And so we want to find the amount of work to do each of these steps, and then talk about the binding energy of the entire alpha particle and per nucleon, and then compare whether that corresponds to any of the steps needed to disassemble the alpha particle. So in the first step, we want to remove a proton. So we can write this as, we want to take our helium-4 and turn it into a proton, which, in order to have the electrons behave themselves, we write as a helium-1 atom, a hydrogen-1 atom, and then a hydrogen-3 atom, because this will have one proton left and then 2 neutrons. And we're conveniently given the masses of all of these things, so it's sort of a hint that this is the right idea. So let's call the energy for this delta E1. So this is going to be the mass of the hydrogen-3 plus the mass of the hydrogen-1 minus the mass of the helium-4 times c squared, because it's an energy. And so this is sort of the final energy minus the initial energy. So that would be the change. And this is 19.8 mega electron volts. It's positive because we had to do work on the nucleus to take the proton out. If this were negative, then alpha particles wouldn't be stable, and you wouldn't find them everywhere. Part B, we want to remove a neutron. Which we can write as taking our hydrogen-3 atom, which is probably quite unhappy about existing. Actually, I don't think hydrogen-3 is that radioactive, but nevertheless, and we get ourselves a neutron plus a hydrogen-2 atom. Here we'll call this delta E2 because it's our second step. And this is basically rinsing and repeating what we did before, except, the masses we're using are different. But conceptually, it's exactly the same thing. Mass of hydrogen-2 times c squared. So this is 6.26 mega electron volts. I think we have enough space to write out step C here, which is to separate the proton and the neutron, which we can write as going from our hydrogen-2 to a hydrogen-1 plus a neutron. This being the third step, we'll call it delta E3. So we have the mass of our hydrogen-1 product plus the mass of our neutron product minus the mass of the hydrogen-2 we started with. times c squared, and this is 2.23 mega electron volts. So now we want the total binding energy. And if you compare the formula for what the total binding energy is versus the three things we just computed, you'll see that it works out that this is just the sum of the three sort of disassembly steps we just computed. You could also just go with the method that was used in a few previous problems calculating the binding energy of various nuclei, but we don't necessarily need to do it in this case. So this is 28.3 mega electron volts. Now we want the binding energy per nucleon. The mass number here is 4, of course, because we have 4 nucleons. And so this is 7.07 mega electron volts. And then we want to see whether any of the first three energies correspond or match one of these two, and they do not. And this sort of makes sense because the binding energy per nucleon is sort of the average of the binding energies that went into assembling the nucleus. It doesn't necessarily reflect the order in which it would come together. And similarly here, the steps of each removal sort of, just the fact that you're not taking it apart completely in one step, of course it's not going to be the same. None of these are going to be the same as the total binding energy. So this makes sense. And we're finished with the problem.